This is problem 7-30E. It's on page 395. The shape shown in figure P7-30 is to be made from extruded plastic and used as a simply supported beam 12 foot long to carry 2 electric cables weighing a total of 6.5 pounds per foot of length. Specify a suitable plastic for the extrusion to provide a design factor of 4 based on flexural strength. All right, if you look at the figure, you'll notice this is a problem that we solved in chapter 6 as an example. And it's one of the reasons I selected this problem, and all I had to do is copy over the spreadsheet. So here it is again. This is the cross-section properties for this problem for 7-30. You can see the location of the centroid measured from the bottom and the area moment of inertia. I'm going to draw it on the board for reference. It looks something like this. And you remember this is one of the cross-sections that I calculated by taking a large rectangle and subtracting out 2 other rectangles. Remember that? I've had several people ask me questions between last class or, I don't know, whenever homework 6 was due in this class, how to calculate cross-section properties, and they usually just had a small mistake in their spreadsheet. There was one group that forgot they had to subtract these areas, so they needed minus signs not only in front of their areas, which you'll notice here, but you also have to put minus signs in front of your area moments of inertia. Okay, so don't forget to do that, and then everything comes out. They had done it right. They drew it in SolidWorks and were verifying their answer. They knew their answer was wrong in the spreadsheet, but couldn't figure out why, because SolidWorks was telling them the right answer. So anyway, the units that we've been given are inches. So the area would be in inches squared, the length, the distance to the centroid, and the area moment of inertia. Good. And I'll try to stop asking you questions you know the answer to. Okay. The reason I do that, the reason I ask those questions is because I think that repetition helps you remember things, and so I'm trying to drill it into you. So anyway, that y distance, that 1.067, you notice the overall height of this thing is 2.4 inches. The height to that center part, let's see, this is not very good. It's not to scale. Let me move this up a little bit. It's going to look more like it really appears. There we go. Okay, let's see, the bottom part, no, the top part of that leg is 1.5 inches. And so the centroid is about here. It's up at 1.0, what is that, 6.7? 6.8 or so inches. Just rounding it off from the spreadsheet. Okay, so that's the location of the neutral axis because it's basically being bent this way. If I were to draw the beam from the side, let's go ahead and make it full size so that it looks like we're just looking at a side view of this thing. The length of the beam, not going to be to scale, but the length of the beam is 12 foot. Whereas you can see that the overall height is 2.4 inches, so my scale is way off. Okay, but you get the idea. And the distributed load on it is a load of 6.5 pounds per foot. So it's just a distributed load, essentially. It looks like this. W is what we usually use for distributed load. 6.5 equals pounds force per foot. And of course, in the real world, probably the way this extrusion is made is so that the cables go in between here. Or maybe they lay in this channel. So is the load actually at the top? No, but it doesn't matter. It doesn't make any difference, right? It doesn't matter at all. So there's our distributed load. We could calculate the total load. We could also make shear and moment diagrams. While we're at it, let's just do all of that. There would be reactions at the end, and I think I computed the magnitude of those. Yeah, I did. They're 39 pounds. I'll leave it to you to figure that out. All you have to do is multiply 6.5 by 12 and then take half of it for each side. Okay? And that would give you your resultant load, or your resultant reactions. And then the shear begins at 39 pounds force. And it's going to move down linearly. Let's see if that's our center point over here. we're going to end up at negative 39. So if I can draw a straight line, it should look something like that. So there's negative 39 pounds force for the shear at the bottom of the, or at the end of the beam. And if I draw the moment, I can actually put the moment on top of this if I draw it in a different color. So the moment in foot pounds force. To do that, all I need to do is add up area, right? So add up all this area, and that would give me the moment at the center of the beam. So since the length from here to here is 6 foot, and the height is 39 pounds, 39 times 6 over 2 would give me the area of that triangle. In fact, so then the moment diagram would look something like that. It's supposed to drop off faster at the end than it is in the center. But anyway, so 6 foot times 39 divided by 2 is a 117 foot-pounds force moment at the center. And I noticed that I had feet here, and I would probably prefer inches, so I just went ahead and multiplied by 12 inches per foot to get 1404 inch pounds force as the maximum moment in the center. Okay? All right, the next bit is to calculate the amount of stress, so the maximum stress. Now, let me ask you a question. Is the maximum stress going to be at this end or at this end? Which section of the plastic is going to be critical? I'll give you a hand. That should tell you the answer. Don't you hate it when somebody writes something down and tells you that should tell you the answer and it doesn't? I mean, it's supposed to be obvious, right? Just write the answer. Well, the answer is whichever fiber is farthest from the neutral axis is the one that's going to experience the most stress. So it's these. Right? Because this height here is below half of 2.5 inches, below 1.2 inches. So the distance from the centroid up to here, or here, is higher than the distance from here down to here. Right? So this C I'm going to plug in to get the maximum stress is the distance 2.4 inches minus 1.068 inches. Does that make sense? All right. So the stress would be the moment. I'm going to plug in the maximum moment because I'm trying to make sure the beam won't fail. I know the beam is not going to fail out at the ends, right? That's not where the load's the highest. I just have to consider the highest in the center. So 1404 inch pounds force multiplied by, let's see, 2.4 less 1.068 inches. Understand what I'm doing there? Is getting this distance. Okay. That's the C in this case because that's the longest distance from the neutral axis. And then I have to divide it by the area moment of inertia, which we get from the spreadsheet, 0.357155 if you want that many decimal places. Say approximately 357 inches to the 4th power. Okay, so we'll get units of PSI because basically, here, let's go through the gory details, shall we? That's what inches to the 4th really means. Inch times inch times inch times inch. Well, move them across off. So it'd be pounds force per square inch. Okay. So this comes out to 4,986.3 PSI, or pounds per square inch, with a design factor of 4, and that means I've got to multiply this by 4. So the design stress would be 4 times that, which is about 19,945 PSI. Okay, so I need some plastic that can take that kind of stress. Now, is this a static load, or should I go back to the other chart? Well, they've essentially given us a design factor, so I'm not going to go back to that table and use a factor there as well. So let's go to the material properties in the back of the book and look for plastics. It's one page past wood. It's page 720. Okay. All right, so let's see. It looks like there's many materials that could could accommodate us. Let's see, there's nylon 66 at 21 KSI. There's polyimide, glass fiber filler at 27, laminate at 50 KSI. So there's several. I just chose nylon 66. Okay. Now, what is the glass fill? What is that? Well, essentially, that's where you're making it into a composite. Have I told you guys about the internship I had with it?
Were you using the tensile strength or the flexural?
I was using the tensile strength. Let's see. They do have flexural strength there as well. I'm not sure why there's a difference. Anyone know? That's something I should know that I've forgotten. I don't know. I'll go back and look it up and I'll find out. And I'll tell you which one's which and why we should use one or the other. Maybe we should use flexural strength instead.
I mean, they said in the problem based on flexural strength. So.
Right, right. But I guess for me, the stress is what's important. And the stress is the same kind of stress. So why there'd be two different, I don't know. I've got to go look it up and find out. Plastics are kind of funny. They act different than metals do. Plastics, well, all the way around are different. They'll creep, which means that you apply a load to them over time and they'll stretch slowly. They also don't melt at just one point. In fact, there's a melting point range. That's kind of interesting. I've had to deal with that before. When I worked for Grody, we were making basically plastic parts, and there was just two layers of plastic. I've forgotten what the plastic was we were using. There were two layers of hard plastic, essentially, that were flexible sheets, and then we used a hot melt glue in between, which was also plastic. And so we were interested in the melting point of the glue. Well, the glue didn't really have a melting point. It had a melting point range. And so we had to do what was called a DSC curve, a differential scanning calorimetry, I think, curve. I can't remember now. But anyway, it was interesting because the way it was performed is they put a sample. They had two chambers that were identical. They put a sample of the hot melt glue in one chamber and nothing in the other. And then they would heat both chambers, but they had controllers on it so that they put in the right amount of heat in order to make both chambers go up in temperature at the same rate. Well, if you got material in one, more mass in one than you have the other, you're going to have to put more heat into it to get it to melt, right? So you got to increase the temperature of the chamber, but you also need to increase the temperature of the stuff you're trying to melt. Well, so if you look at it as the plastic melts, what happens is it starts to suck up a lot more energy because you're trying to change the temperature, but you can't because there's a phase change there. And so you've got to dump a lot more heat into it. And so you're dumping a lot more energy into one chamber than the other. And if you record the amount of energy draw required, then you can see how much it took to melt it. But there's actually, from it, you can see a melting point range, which is kind of interesting. So anyway, the point is that plastics behave very differently, and I don't know the answer to that question, but I'll find out. What was I going to say? Oh, the internship I had. I worked for a company called Banjo Corporation. Have I mentioned them to you before? I think I did. Did I show you their products? Oh, I did. Okay. Well, anyway, their product is essentially I'm sorry, I can't remember who I've told what, so help me not repeat myself. It's like bad jokes. They keep coming back down. Anyway, they made their products out of a glass-filled plastic. So it was a composite, essentially. So they would injection mold plastic full of basically glass fibers, if you will. And that greatly increases the strength of the plastic. And it's pretty interesting stuff. But anyway, any questions on this example problem? Anything else I need to discuss with you about it? I think so far students have asked most questions about how to come up with this because they're trying to come up with the moment and they realize they've got to do something. They've got to somehow go from load to moment load. Just don't forget you can make shear moment diagrams. That's the key to coming up with the moment. Okay.